Hey guys, welcome back to the Blimp video channel. My name is Craig Enders and I appreciate you tuning in. In this video, I'm going to talk about outcome variables. Blimp offers modeling for normal and non-normal continuous variables, as well as a variety of discrete metrics. In this video, I'm going to show how to specify different link functions, and I'll paint the broad brushstrokes behind the latent response formulation for discrete variables. Before we get started, I want to acknowledge the Institute of Educational Sciences for their support and point you to the project's website. You can download Blimp at the same homepage. Click the subscribe button in YouTube to receive alerts when I post new videos to the page. Okay, so let's jump in. Blimp allows for a variety of different variable types. Continuous outcomes can be normal, positively skewed, or negatively skewed. Discrete metrics include binary, ordinal, multi-categorical nominal variables, and count variables. These outcome types are available for both single-level and multi-level regression models with up to 3 levels. You can also have multiple indicator latent variables as outcomes. In this video, I'll focus on manifest variables, and I'll take up latent factors and path models in another video. In a previous video, I explained that Blimp uses a factored regression specification that divides a multivariate distribution into a sequence of simpler distributions. Beyond acknowledging that the multivariate distribution exists, factorization makes no assumptions about the shape or form of the distribution. Rather, assumptions enter on a variable by variable or model by model basis. Tailoring distributional assumptions in this way allows us to mix and match metrics within the same model. In this video, I focus on a factorization that assigns a multivariate distribution to the predictors. The outcome has a distinct univariate distribution that can be different. In the path diagram, I have the two predictors and outcome in different colored sandboxes to convey that Blimp is invoking two distinct statistical models, each with its own assumptions. In this video, I'll focus on outcome variables with incoming directed arrows. Looking at the model command on the left, the outcome variable is to the left of the tilde and the predictors are to the right. By default, Blimp assumes that dependent variables have normal residuals. The way we accommodate categorical variables is through the latent response variable framework. For example, a binary variable imagines a normally distributed latent variable with a single threshold cut point that divides the continuous distribution into 2 segments. An ordinal variable is similar but has multiple threshold parameters that divide the distribution into groups. Finally, multi-categorical variables use multiple latent variables that are analogous to continuous versions of dummy variables. The diagram shows a 3-category nominal variable that requires a pair of latent response variables. Let's take a closer look at a model with a binary outcome. Designating a variable on the ordinal line invokes a probit regression. The probit model essentially defines the latent response variable as a normally distributed z-score. The path diagram uses an oval to represent the continuous latent variable. Notice that the predictor arrows point to the latent response variable. Finally, the broken arrow represents a nonlinear link function that maps the latent variable to the discrete outcome and the probability metric. To make the illustration more concrete, I'll use data from an educational study where the goal is to determine whether broad reading scores from 1st grade predict 9th grade reading proficiency. The regression model looks like this. The reading proficiency outcome is binary with 0 and 1 coding below average and average reading levels. The asterisk superscript in the equation on the dependent variable denotes a latent response variable. In this data set, about 48% of the students are classified as average readers in 9th grade and 52% are below average. The graph on the right shows the latent reading proficiency distribution. The threshold parameter divides the continuous distribution into 2 segments such that the areas under the curve match the bar plot proportions. Because the latent variable is unobserved, its conditional variance is fixed at 1 to establish a scale, and the threshold cut point is fixed at 0 to identify the mean part of the model. The latent variable mean is an estimated parameter in this case. In the graph, the mean is slightly negative because the threshold has to be above the mean in order to get 48% in the upper tail. So let's take a look at the regression model. The probit regression describes the association between 1st grade reading scores and the latent reading proficiency variable for 9th grade. Consistent with the previous graphs, students with average reading in 9th grade have latent scores above the threshold, and students who are below average in 9th grade have latent scores below the cut point. I color code the dots in the scatter plot to emphasize this point. In another video, I explained that Blimp's MCMC algorithm cycles between two broad steps. The first step estimates the model parameters, and the second step uses those parameters to derive distributions of missing values from which the algorithm samples imputations. Categorical variable models are actually the ultimate missing data problem because the latent response scores are missing for 100% of the sample. MCMC imputes those values at every computational cycle, regardless of whether the discrete classification is observed. Let's take a closer look at how imputation works with the binary reading variable. To begin, let's think about latent variable imputation for a student with average reading in 9th grade. Remember that the probit model requires the latent variable scores for such a student to be above the threshold parameter. The graphic shows the latent variable distributions at 3 levels of 1st grade reading. Notice that the normal curves are chopped off or truncated at 0. The black dots are the predicted latent variable scores from the regression model, and the white circles are plausible latent variable imputations, MCMC sample scores at random from these distributions. Next, let's look at latent variable imputation for a student with below average reading in 9th grade. This time the probit model requires that the latent variable scores are below the threshold cut point. The graphic shows the latent variable distributions at 3 levels of 1st grade reading. So again, notice that the normal curves are truncated at 0, but this time in the upper tail of the distribution. The black dots are the predicted latent variable scores from the regression model, and the white circles are again plausible latent variable imputations, MCMC sample scores at random from these distributions. For students with missing data in 9th grade, we don't know the value of their discrete classification, so we don't know which region of the curve the latent score should fall in. In this case, we lift the restriction and allow the latent scores to fall anywhere in the normal curve. This graphic shows the latent variable distributions at 3 levels of 1st grade reading. This time, the imputations, which are the white circles, are completely unbounded. The imputation process actually provides a pair of scores, one on the continuous latent variable metric and one on the discrete metric. To illustrate, consider imputation for a student with a relatively low 1st grade reading score. The white dots are the imputations for this person. MCMC randomly samples a continuous score from that normal distribution. The orange dot is the imputed value from a particular computational cycle. Because the dot is below the threshold, we can also infer that the discrete imputation should equal 0. At this particular iteration, the algorithm classifies the student as below average in the 9th grade. It's important to emphasize that Blimp is not simply treating the discrete variable as normal and rounding the continuous impute. Rather, a link function is what's mapping the latent variable imputes to the discrete metric. The discrete imputations for each individual can vary from one iteration to the next to account for uncertainty. For example, in this diagram, the latent imputation falls above the threshold. This location for the continuous impute logically implies that the student has a discrete score of 1, which indicates above average reading. The ordinal command is appropriate for any binary variable, even ones where the categories don't have an inherent order. You might have guessed that this command also accommodates ordered categorical variables with more than 2 levels. Likert or Likert type rating scales are a common example. To illustrate, the bar graph on the left displays the responses from a 4-category rating scale. The normal curve on the right is the latent variable distribution. With 4 categories, it now takes 3 threshold parameters to divide the continuous distribution into 4 segments. As before, the areas in each segment of the curve correspond to the category proportions from the bar graph. Looking at the Blimp syntax, nothing changes with an ordinal outcome. The software determines that you have more than 2 categories, but the model setup stays the same. It's important to note that ordinal variables require much longer burn-in periods to achieve convergence because the threshold parameters are difficult to estimate. Depending on the number of variables and the size of the data set, burn-in periods of 20,000 to 40,000 iterations could be perfectly normal. Finally, when using the save command to create multiply imputed data sets, listing the save predicted keyword on the options line writes individual level predicted probabilities for each category. Probit models are simple to think about because the latent response variable is scaled like a z-score. However, many of us instead learned about logistic models in our regression classes. Although we might not have learned it this way, logistic models can also be motivated by an underlying latent variable. The latent variable's error distribution is symmetric, but it's no longer a normal curve. Blimp offers logistic regression for binary and multi-categorical outcomes. Let's revisit a regression model with a binary outcome. Specifying the nominal command invokes a logistic rather than probit regression. The model summary in the Blimp output file adjusted this change by printing odds ratios instead of standardized coefficients. The setup for a multi-categorical nominal variable is the same. The outcome variable is simply listed on the nominal line. The path diagram depicts the model for a 3-category variable such as below average, average, and above average reading levels. The nominal model does not utilize thresholds anymore. Rather, multiple latent variables represent the categories. Like dummy coding, each latent variable represents a contrast between one of the groups relative to a reference category. The path diagram shows a situation where the predictors influence the propensity for classification in groups 2 and 3 relative to reference category 1. Blimp automatically assigns the lowest numeric code as the reference group. You can change this by listing the desired reference group code on the nominal line. In this example, I designate group 3 as the reference group. The latent variables now represent the propensity for classification in groups 1 and 2 relative to reference category 3. We have 2 more outcome types to look at: count variables and non-normal continuous variables. For count outcomes, Blimp offers negative binomial regression. This procedure can be viewed as an extension of Poisson regression that allows for unobserved heterogeneity. The model achieves this by introducing a dispersion parameter that essentially allows people with the same predicted score to have different observed counts. The interpretation of the model parameters is otherwise the same as a Poisson regression. In the Blimp syntax, you invoke a negative binomial regression using the count command. Blimp's MCMC algorithm uses a latent response variable during estimation, but this is more of a computational convenience as the individual scores don't have a substantive meaning. Nevertheless, it's useful to think about the outcome as existing in a continuous and discrete state, as you would in a generalized linear model. Non-normal continuous variables are the final outcome type. Blimp uses a transformation procedure based on the Yau-Johnson normal distribution. In this case, the latent variable is essentially a normalized version of the non-normal manifest variable, and a shape parameter that works like a length function maps the normalized scores to the skewed metric. The Yau-Johnson procedure subsumes common methods like logarithmic and Box-Cox transformations, but it's more convenient because we don't have to choose a transformation in advance. The shape parameter is iteratively estimated according to the shape of the observed data distribution. We also don't need to rescale variables to avoid 0 because the Yau-Johnson procedure allows for positive and negative scores. So let's take a look at the Blimp code for this. To invoke the Yau-Johnson transformation, you simply list the dependent variable's name inside the yjt function to the left of the tilde. The path diagram on the right emphasizes that the predictors are influencing the normalized version of y, and the broken arrow represents a nonlinear function that maps the normalized scores to the skewed variable. My experience suggests that the Yau-Johnson procedure converges more reliably if the outcome variable has a 0 in its range. In cases where 0 is not a legitimate score, I usually center the variable at its median. For example, suppose that the non-normal outcome variable had a median of 10. The code on the slide simply subtracts a value of 10 from the dependent variable inside the parentheses. We don't need to create a new variable. This can be done on the fly. Finally, when using the save command to create multiply imputed data sets, listing the save latent keyword on the options line writes the normalized scores to the file. By default, only the non-normal manifest imputations are saved. That concludes the brief tour of outcome variable types in Blimp. In another video, I dig deeper into this topic and show what happens when you have predictors with mixed metrics. Thanks for tuning in, and I hope you check out future videos.